Okay, so welcome to this second part in the video on independent random variables, and now what we're going to see is that the binomial distribution is effectively the sum of n independent, identically distributed Bernoulli P distributions. Okay, so we have discussed our sample space being this set of all possible outcomes of tossing a coin n times and getting either heads or tails. So the binomial distribution, if we wanted to map this onto the binomial probability space, what we would do is we'd say set up some random variable, let's call it y, and we'd say let's map. Firstly, let's partition this set up into events. So let's have the event that you get 0 heads, the event that you get 1 head, the event that you get 2 heads, the events that you get all the way up to n heads. And then what we do is we map each of those events. So we map it onto the number that it corresponds to of getting heads. So we map it onto 0, 1, 2, 3 all the way up to n, and we've seen that when we do that, the probability mass function, so the probability of if you stick each of these outcomes in a set by itself, that probability is given by let's say for an arbitrary I, it's given by p to the power of I 1 minus p, and a notation that you'll often see for 1 minus p is q, so I'll start using that, q to the n minus I, n choose I. Okay, where p is the probability of getting a heads and q is the probability of getting a tails. Okay, so now what I want to show you is that probability mass function can be constructed. The way that you can think of this is as the sum of n identically distributed independent Bernoulli P distributions. So I want to show you how. So here's a new piece of paper. Yep, we do need a new piece of paper. Okay, so I'm just going to recap what we've done so far. We have our probability space here, our abstract probability space, which has every single possible outcome of tossing a coin n times. So, all the way up to, let's say that, and you toss it n times. Okay. So, we could define other random variables on this. We could define Bernoulli random variables on this. So let's let x1 be the Bernoulli. Let's let this be another random variable, and it's going to split the set into two things. So all the outcomes that you get a heads on the first flip. So partition the sample space into 2 bits, basically. Let one event be the event that you get a head on first flip. So effectively it's the equivalent of what we have back here, but on a bigger scale. So we split this, and then we had this event that you got a head on the first flip, and this event that you got a tail on the first flip. So we're going to let this be the event that you get a head on the first flip. So all of the outcomes which involve a head on the first flip go into this one, and all of the outcomes that you get a tail on the first flip go into this one. Tail on first flip go into this one. Okay, and then basically what I want you to do is map that set. I want that set to be mapped onto 1, and I want that set to be mapped onto 0. And this time we said that the probability of getting a head was p. So this will be a p, and this will be 1 minus p, which we said was going to be called q. So this is a Bernoulli P distribution. So x is distributed Bernoulli P. X1 rather is distributed Bernoulli P. So that x1, remember, is this random variable, this function mapping this abstract probability space onto this probability space here. Now you can define more of these Bernoulli probability spaces, because we can why just bother about the first one? Instead, we could go again. So I need another color pen. Let's instead split it another way. So let's split it down here this time, and let's split it up into the events that you get a head on the second flip rather, and a tail on the second flip. So every outcome either has a head on the second flip, or it has a tail on the second flip. So it's either in this event or this event. So let this be the event that you get a head on second flip, and let this be the event that you get a tail on the second flip, tail on second flip. Okay, and then take the random variable x2, which is going to map the event that you get a head on the second flip onto 1, and the event that you get a tail on the second flip onto 0. And the probability of the event that you get a head on the second flip is just p, and the probability that you get 0 is q. And you can go on. Let's define x3 to be equal to the random variable, which is going to map this onto, again, the same probability distribution again, 1, 0, pq, like that, and it's going to map the event that you get a head on the third flip onto 1, and it's going to map the event that you get a tail on the third flip onto 0. And we'll do this all the way up to xn, so that, and all of these are exactly the same probability space. So that is what we mean by n independent. Oh well, I haven't shown that independent yet, but I've shown the ID bit of IID. Identically independent, identically distributed random variables. Okay, so xn are n independent, identically distributed random variables. Okay, so why are these independent? Well, they independent, the way you should view what independence means is it means that the result of this one does not affect the result of this one, and it's intuitively obvious that these trials are independent, because getting a head on the first flip doesn't affect your probability of getting a head on the second flip, or getting a tail on the second flip. So they are independent. It would require a lot of work to show that they are independent, because you would have to go through every possible combination and make sure that they are all independent. But intuitively, it's pretty obvious that they're going to be independent, because if you take, for instance, the event that you get a head on the first flip and you get a tail on the second flip, and then you can get anything after that, it's pretty obvious that that is going to be PQ. The probability of that is going to be PQ, which is the probability of getting a head on the first flip times the probability of getting a tail on the second flip. I know that's very hand-wavy, but they are independent. So if you believe that they are independent, then these are independent, identically distributed random variables, and we can define some interesting stuff. So we could define a new random variable, which we could call x1, which would be equal to x1 plus x2 plus all the way up to xn. We could add all the values together, basically, and we could say, how is this distributed? How is the sum of values 1 or 0 distributed? Which will what will this value be? This will be the number of ones you overall get. The value of this will be the number of ones you get, which will be the number of heads you get. So this would be equal to the number of heads you get. So we could ask, how is this distributed? And we'll continue this video in the next part.